Hello students, welcome to chemistry class. Here with you is Oyelami Janet today, and today we're going to be talking about most of the interesting topics. We've actually treated some of them, but today we're going to be looking at pure calculation underneath each of them. So we're going to be looking at valency calculation, ions, atomicity, percentage composition, and isotopic abundance of elements. So as I always tell you, make sure you are sitting at a very conducive area free of noise and distraction, so we can have a sweet and wonderful class together. So to our objective for today, all we need to know at the end of this class, we should be able to calculate valency. Okay, that's one. We should be able to calculate ions, different ions in a compound. That's another one. We should be able to calculate the atomicity of an element, as well as calculating the percentage composition with isotopic abundance of an element. So valency, as we all know that the valency of an element is the number of hydrogen atoms that will combine with or displace an atom of that element. Okay, so you can as well say the valency is the combining power of an element when compared with hydrogen. It is normally a whole number. You can't see it in a fraction or decimal, what have you, but it's always in a whole number. So an element can be monovalent, univalent, trivalent, tetravalent, polyvalent, as the case may be. So you have some elements here with their examples. So to determine the valency of an element, the following should be considered. Number one, the number of valence electron or outermost electron of the element. You know, many times, most of you normally confuse valency with valence electrons. There are two different things, okay? Valency, as we defined earlier on, is the combining power of elements. Why this valence? When you talk about valence electron, you are talking of the electron in the outermost shell of that element that can be used in bonding, okay? They are different. There's a thin line between them, so you have to know that. So in determining valency of an element, you must take care of these three things. So the first one is that the number of valence electron or outermost electron of the element, you have to know it. Then you have to know the group the element belongs, okay? You have to know the number of electrons required by the elements, usually non-metal, to acquire the filled electron structure. So we have some examples there. The first one, determine the valency of the following element. For sodium, having atomic number of 11 and atomic mass of 23. Same thing with oxygen, 816, and chlorine, 1735. So how do you think you can do it? Follow my solution here. So for sodium, electronic configuration, you know, this atomic number, okay? So you can try to do this. Either you do it in orbital distribution, or you do it in your normal 2-8, having your KLM NOP shell. Okay, so for sodium now, having atomic number of 11, so it will have it has 2 electrons in the K shell, 8 electrons in the L shell, and 1 electron in the M shell. So definitely the combining power of sodium, which is 1. That's why I wrote valency to be 1 here. Same thing if you look at oxygen, we have electronic configuration. You know, the atomic number is 8. Okay, the subscript here is 8, so you have to distribute it into shell. So, you know, this calculation of maximum number of electrons in each shell, that's for another day. We're going to look at that very soon. So, distribution of oxygen is 2 and 6. So, definitely it has a valency of -2. Why is it -2, if I may ask? You know, we said is distributed in K shell to be 2 electrons. That's maximum number of electrons in K shell. And this maximum number of electrons in L shell. So for L shell to be filled up, it's remaining 2 to reach the octant configuration. And you know, atoms of elements are always stable when they are half filled or filled when they are having filled electronic configuration. So the valence on a normal day, the valency number of oxygen is supposed to be 6 plus 6, but it could be -2 because it needs 2 electrons to be in a stable state. So it prefers this very valency of -2. So the valency of oxygen is plus is because it has 6 valence electrons, okay? And the valency of oxygen is -2 because it needs 2 electrons to acquire a filled electronic configuration. I hope you understand what I just... So when it's received 2 electrons, it becomes oxygen, it becomes negatively charged atom. So here for chlorine too, same thing. Chlorine is 17287, so it has valency of +7, but you know, because of the affinity for electron, they prefer to exhibit this -1 valency state, because it's easier for them to take 1 and become stable than to lose 7. They can't give out electron, but they can easily receive from mainly melter group. So determination of valency from molecular formulae. So there are some formulae in which you can determine your valency from. For instance, we have example here. We have determined the valency of underlying elements or radical in their compounds. For instance, iron in iron 3 chloride. So for you to determine that, you must make sure that you equate the whole compound to 0. So it will be easier for you to determine that. Same thing in B part, you have to determine the valency of sulfur in tetraisosulfate 6, then valency of sulfur in these two. So we have to do that in this solution. The first one, which is determination of iron in iron 3 chloride. We all know that since chlorine has -1 as its valency number, you know, that's the combining power -1 to reach octant state. It must always collect 1 electron. So for the three atoms of chlorine, that makes it -3, which definitely you must know that you must have a +3 to negate that effect, to give you the compound, the neutral compound, which will be 0. Okay, same thing with this second one, which is sulfur in tetraisosulfate 6, and same thing with sulfite 1. So we move to this is a table showing first 30 elements from atomic number 1 to 30. So here you can see the atomic masses as well as their valency number. Okay, so this is another one of which we are going very fast into the iron now. This for iron, you have to know, we treated it earlier when you have the one that carries positive charge is called cation, and the one with negative charge are called anion. So this ion, an ion is charged atom or molecule. It is charged because the number of electrons do not equal to the number of protons in the atom or molecule. So an atom can acquire a positive charge or negative charge depending on whether the number of electrons in an atom is greater or less than the number of protons. You know, when you have deficiency of a proton, definitely the element or the compound will be negatively charged. Same thing if you have deficiency of electron, the compound will be positively charged. So positively charged ions are called cation, while negatively charged ions are called anions. So here are the examples. You have them there. You can always take your time and look through. You have the negatively charged ions, which are the anion, and the positively charged ions, which are the cations. So on a normal day, when you have an atom, is always neutral. Like I said, for compound, when we were calculating the valency number of each compound the other time, everything is supposed to be neutral. But when there is loss of electron, you have the cation. When there is gain of electron, you have the anion, which is negative charge. So radicals. There are some compounds, or there are some group of, you can call them group of atoms or atoms. They behave as one unit. They behave like a single unit, okay? They are called radicals. Radicals are defined as atoms or group of atoms carrying charge. Okay, they could carry positive as well, they could carry negative. E.g., you have what we call the NO3 2 minus. Okay, you can have CO3 minus, something like that. Those are examples of radicals. So here, to calculate ions, these are the procedure. This is the first examples. When you're talking of hydrogen phosphates here, you have the this is the equation. So it will dissociate to give you what? 3 hydrogen ions, and you have triphosphate ion here too. So from the equation, you can see it's only one. Is because they are not writing it there, but it's one mole of this compound will dissociate to give 3 moles of hydrogen ion and 1 mole of phosphate ion. So when you are being given from, okay, sorry about that. This is the question. So when you are being given, you are being told to calculate the mass of hydrogen and tetraisosulfate cis ion present in 250 cm cube of 0.2 molar of hydrogen phosphate solution. So how are you going to do that to calculate? These are the ions you are being told to calculate. You have to calculate the hydrogen ion, the mass of hydrogen ion, and the mass of tetraisosulfate 5 ion. Okay, so in order to do that, you have to follow this very procedure. You have to follow the procedure I'm showing you in a bit in order to calculate that. Okay, so let's look at it together. Number of moles, you all know that this is the formula. Number of moles in solution equals to concentration times volume. Okay, when the volume is being given in cm cube, you have to make sure you convert it to dm cube by dividing by 1000. Okay, when you divide this 250 by 1000, what do you have? You have 0.2 0.25. So 0.25 times 0.2 will give you what? 0.05 moles. That mole of the compound. Don't forget, I showed you the compound. This is the compound, and this is how it's been dissociated into their respective ions. So from what we calculated from the equation here, you can see that one of these, we give 3 of these and 1 of this. And from our calculation, we got this compound to have 0.05 moles. So comparing it to other ions, that means when this one is 1, this one is 3. Then when this one is 0.5, this one will be 3 times 0.5. And this one will be 1 times 0.5. So definitely 0.15 mole of hydrogen ions will be formed, and 0.05 mole of phosphate ion will be formed. And to calculate the mass, you know, from your number of mole equals to mass of whatever being given divided by molar mass, or 1 mole of that compound or that element, which I did here. So in order to get our mass, you make your mass the subject of the formula, which makes us to get something like this. Okay, same thing with phosphate ion. You're going to follow the same formula to achieve same results. So I want you to try this on your own and see maybe we are on the same page. Okay, atomicity of an element is the number of atoms present in 1 mole of that element. You know, we did it like 2 classes before now, and the usefulness of this is to bring back what we've done and to do the calculation on it. We are not just doing the theoretical part. We are not going into theory right now, but we want to try to lay our hands on some calculations about this atomicity. So an element can be mono or atomic element, could be diatomic, could be triatomic, could be poly, like 4, like 5, and all that. So all these we've seen in the previous class. So now we want to determine the atomicity of elements. How can we do that? We have to follow all these steps I made mention here. The first one is that the relative molecular mass of vapor density, you have to know that. Okay, and the second one is that you have to know the relative atomic mass. Okay, how are you now going to do that? We always know that relative molecular mass, which is same thing as our relative formula mass, any day, anytime, equals to vapor density times 2. Okay, to now know the atomicity of an element, you have to do your relative molecular mass, which is acronym of RMM, divided by what? Relative atomic mass, which is RAN. So we have to look at a question. A question says, determine atomicity of each of the following elements. An element with relative molecular mass of 160 and relative atomic mass of 80. So when you use the formula, this is what you have. You have it 160 divided by 80, which will give you 2. That means the element has atomicity of 2. And at the same time, here you are just being given a vapor density and relative atomic mass, no relative molecular mass. And from the previous formula, I said relative molecular mass is vapor density times 2. That times 2. So that's what I'm using right here. Vapor density times 2 divided by relative atomic mass. So 62 times 2 divided by 31 will give you 4. Okay, percentage composition. You can know how to calculate percentage composition of a compound by following this procedure. The first thing we have to know is we have to calculate, in order to get our percentage composition, we have to get this by calculating the relative molecular mass of the compound, as well as calculating the amount in percentage of the elements in the compound. So I want you to note that the percentage composition of each element in the compound must add up to approximately 100. Okay, when you add up all the elements in a compound, as in their percentage composition of each element in compound must be, if it's not equals to 100, must be approximately 100. Okay, let's look at this example. Calculate the percentage composition of the elements in the following compound. So the first one says calculate the percentage composition of calcium triisocarbonate 4. That's Caco 3, which is your limestone. And the second one is that we should calculate the mass of sodium hydroxide. Okay, so I'll do the first one for you. I want you to try that second one on your own, because it will be a good thing when I do an example. It's better to replicate that very problem by trying it on your own. So the solution for the first one is calcium triisocarbonate 4. Here you have the relative molecular mass of Caco 3. For calcium, you have it to be 40, for carbon 12, for oxygen 16, and we have 3 atoms of oxygen, so definitely it should be 16 times 3, which will give us a total relative molecular mass of 100. So when you now want to calculate the percentage composition of calcium in this compound, so it will be relative molecular mass of calcium divided by the overall molecular mass, relative molecular mass, times 100. That's what I did here. So for calcium, it's 40 divided by overall molecular mass, which is 100 times 100. So it will give you 40%. Same thing, you try for carbon, for oxygen. So if you look at the 3, 40 plus 12 plus 48, that's 100%. So try for sodium hydroxide and let me know what you get. So isotopic abundance of an element. This is the amount in percentage of isotopic form of an element in nature. Okay, you know, when you talk of isotopic form, you have some elements that has same atomic mass but different atomic number due to difference in the number of their neutrons. Okay, for example, natural oxygen has 3 isotopes. Okay, the first one is oxygen 816, which has 99.76%. Then oxygen 817 has 0.05%, and likewise the 18, this one should be 18, so which has, it has 0.02 of that. So the relative abundance of each isotope can be used to determine the relative atomic mass. So when you find the relative abundance, isotopic abundance of all the isotopes of oxygen, you get what? Relative atomic mass of oxygen in this case. So note, an element can exist in more than two isotopic form. So I have a table showing you different isotopes. We have here, we have hydrogen, the 3 are here, carbon, the 2, nitrogen, like that. You can take your time and study. Those are the different types of isotopes of elements that we have. And it might not be that much, but at least with this, you know much of it. Then this for hydrogen, I just replicate for hydrogen, this hydrogen 1, which is protium, this deuterium, this tritium, okay, tritium. So when you look at the 3, you know that the difference between the 3 is the neurons. The number of neutrons in each of them differs, okay. For instance, you have the first one has what? 0 neutron. The second one has 1 neutron. Then the third one has 2 neutrons. So that is what accounts for the three forms that they have. So example, an element T exists in two isotopic form in ratio 2:3. So if the isotopes have their relative atomic mass as 15 and 17 respectively, calculate the relative atomic mass of element T. So the first thing you are going to do when you want to calculate this is to add up their ratio. Their ratio is 5, 2, and 3. So you now take them one by one, just like we know how to do that in maths. So 2, the one for ratio 2 will be 2 over what? 5. This should be 5. Okay? So that's 2 over 5. Okay? 2 over 5 times the first one represents for ratio 2. So 15, that will be 2 divided by 5 multiplied by 15. Then plus, that's how to add it. If you have like 10 isotopic form of that element, you keep on adding them. So 3 over 5 divided by 17, which is the second one, will give us, this one will give us 6, and the other one will give us 10.2. And the addition of the two will give us 16.2. So that's the relative atomic mass of that element. Okay? So this is another example. Example 2 say natural lithium consists of two isotopes, which is 7.4 of lithium and 92.6 of lithium 7. Determine the relative atomic mass of natural lithium. So to do that, you follow same procedure. Percentage 7.4 divided by 100. You know, this one is different from the first one we did. This one is in percentage. So it will be 7.4 divided by 100 times, you have been given the mass number or the atomic mass to be what? 6 times 6 plus 92.6 times what? You have been given this one to be 7. So times 7. So your answer will become 6.926. So I want you to try this class drill. The first one says write down the atomicity of the following elements for helium, for sulfur, for iron. So you have to write it for me, atomicity. Write how you get it, and I would like to save that. And same thing, zinc has valency of 2. Write down the molecular formula of tetraisosulfate 6 and triisocarbonate 4. So you have to calculate that. I guess we don't need this after all, because the one I gave you is not including zinc. So you just have to do that. Try to calculate, write down the molecular formula of this and calculate the valency of each of them. Okay? And same thing with the third one. Calculate the percentage composition of a hydrogen tetraisosulfate 6 and chlorine in iron 2 chloride. Then the last one is that an element Y exists in 3 isotopic form in ratio of 2, 3, and 4. So if the isotopes have their relative atomic masses as 29, 30, 31 respectively, calculate the relative atomic mass of the elements. So virtually everything I've done, and we've done it together. So I know this one will be as simple as other solution. And before I close, I would like to tell you, as much as you watch the video, make sure you take part in the class activities by doing your quiz and try to, 99.9% of what we do, we don't write them down or try to do it on our own, it's probably will not stick that much. But if you take part, you try to solve, you try to lay your hands on questions and try to evaluate how well you are good in that topic, it won't be part of you. You might just look at the video and feel you gain something, but try as much as possible to lay your hands on questions involving that topic. And as we all know, there's always class activities for you at the end of this class, so make sure you do them and take part actively. Stay blessed and be happy. Enjoy your day. Bye.